I would like to give my presentation, my paper titled Lightweight Dual Polarized Horn Antenna for Polarimetry Shape SAR Sensor on Board UAV. My name is Agus Hendra Wahyudi. I'm young researcher in Research Center for Aeronautic Technology, National Research and Innovation Agency or BRIN. Together with my friends as co-author Farohaji Kurniawan, Bambang Setiadi, Agus, Wiyono, Satria, Arief, Aditya, Widada, and Effendi, Dodi, Arisandi, all is from BRIN. Okay, first of all, I would like to present the abstract. UAVs can collect Earth surface information with SAR sensors during night, day, and bad weather. However, UAVs have only limited volume and weight for the SAR payload. A very light dual circularly polarized pyramid horn antenna was developed in order to improve sense capability in UAV dual polarimetry SAR images. The pyramid horn was designed and simulated in GST 2022. The horn was capable of producing two circular polarized antenna RHCP and LHCP alternately using a three-step septum polarizer and coaxial probe feed on two sides of the waveguide. The result shows that the horn antenna was capable of having a wide S11 and S22 bandwidth from 4 to 6.7 GHz. The horn was capable of producing two polarization with axial ratio below 3 dB from 4.4 to 6.4 GHz. This gain horn antenna was relatively stable in the range of 15 dBIC. And the reasonable the beam width, 3 dB beam width is 28 degrees both RHCP and LHCP polarization in the A and H speed respectively. Next, the introduction of this paper. UAV are increasingly demanded by remote sensing users for mapping purposes. One of the active remote sensing sensors in UAVs that can work with various weather, day and night is synthetic aperture radar, as mentioned in reference number 1 until number 4. In order to improve detection on the SAR application, two types of SAR image that have different polarization are used: vertical and horizontal, or circular to the left and circular to the right, as mentioned in the literature number 5 until number 7. Circular polarization has advantages for SARs in UAVs over linear ones. It is more resistant to polarization mismatch interference due to changes in antenna position in the UAV, and can provide additional information in the form of inclination angles and improve SAR image detection, as mentioned in literature number 5, 8, and 9. However, small UAVs have limited space and weight of SAR payload that can be used. Therefore, a lightweight SAR sensor antenna is needed, and a relatively small size according to the dimension of the UAV. The antenna must also have high gain and wide enough bandwidth, as well as the ability to work in two polarization to produce SAR image of two different polarization. A horn antenna is very appropriate for these characteristics because it has a lightweight structure when using 3D printer fabrication methods and large gain, dual polarization, and wide bandwidth. Microstrip antenna are capable of producing circular polarization waves with the wide bandwidth also, but have a small gain for single element. For example, less than 5 dBi in literature number 10, 11, and 12. Increasing the gain of the microstrip antenna can be done by arranging it in an antenna array, as mentioned in literature number 1 and 13. However, this will increase the antenna area and weight, which is very limited for small UAVs. This study aims to investigate the design and use of a 3D printed dual polarization pyramidal horn antenna in the SAR system that will be used later in small UAVs. The horn performance was adjusted to the existing SAR system in our office, namely the middle frequency at 5.3 GHz and gain 15 dBIC with bandwidth more or equal than 300 MHz. So the resolution was high enough for Earth surface mapping applications. Okay, next is the research method. In design the horn antenna, a pyramidal horn antenna type with a square waveguide in the C-band was used. The method of determining the dimension of the horn antenna, for example, the length of horn and then the aperture A and B, as we can see here in figure 1A and B, Begin with optimum gain and waveguide dimension as described by literature number 14, Balanis, the antenna model analysis and design. In order to produce dual polarized circular wave, step septum polarizer was inserted in the middle of the waveguide. See figure 1A and B, which function to change the linear polarization mode TA01 in the rectangular waveguide section to circular polarization in the square waveguide in front of the neck. And circular polarization can be achieved at the desired frequency by adjusting the width and height of the step on the septum. So this parameter is L and H, as we can see here in figure 1A. As demonstrated in other many literature, for example, literature number 15 until 20, also use the step septum polarizer method. In addition, other methods such as the single reach, as mentioned in literature number 21, and double reach in literature number 22 can also produce circular polarization wave. However, reach polarizer in dual polarized horn antenna may produce poor isolation because there is a coupling between ports. In our dual port antenna, the waveguide was excited with a coaxial probe feed, with the dimension of the probe length and distance to the cavity set to that so that the resonance was centered on the working frequency of the SAR system. In this case, 5.3 GHz. The simulation and design were carried out with professional GST 2022 software. Optimal antenna parameters after intensive simulation were obtained values as in table 1 here. The parameter of the step septum, the value, and this is the symbol, the cavity, aperture, and the waveguide, all is mentioned in here in the table 1. The optimal values of antenna pyramidal horn CP parameters. The basic material of the horn antenna structure of figure 1 used an ABS filament 3D printer, which is a polymer that has a dielectric constant of 2.6 and a loss factor of 0.018, as mentioned in literature number 23. The horn structure is coated with the conductive paint mixed with silver and copper, Mg843AR 340G, which has a resistivity of 0.00022 ohm centimeter based on the datasheet. The thickness of 0.3 mm of the conductive paint was chosen, and it is thicker than the skin depth of the working frequency. The result and discussion. Next, we will present the result of our simulation with CSA software. So in this section, we will analyze the antenna bandwidth, gain, adjacent pattern to determine the characteristic of our antenna. Antenna bandwidth. The antenna bandwidth criterion was determined by setting the S11 and S22 values less than minus 10 dB. The isolation port was evaluated based on the S21 and S12 values. The simulation result, as shown in figure 2 here, indicate that the horn antenna exhibited a bandwidth covering the frequency range of 4.55 GHz to 6.67 GHz. In the SAR system working range for the C-band, the isolation value between port remain below minus 20 dB, as indicated in S21 and S12. The excellent isolation between port, which was maintained below minus 20 dB, can be attributed to the presence of the septal wall separating the two ports, preventing underside coupling between them. The performance of the antenna in the C-band was also supported by the well-functioning S11 and S22 values. This was achieved by adjusting the feeding probe length to correspond to actuator resonant frequency wavelength. Additionally, the probe to cavity distance was set to approximately actuator wavelength of the central frequency, which was 5.3 GHz. Apart from the S parameter values, the bandwidth of an antenna with circular polarization should also meet the criterion of its axial ratio being less than 3 dB. Figure 2 present the simulation result indicating that the bandwidth of the axial ratio of circular polarization span from 4.4, here the line of 3 dB, 4.4 until 6.25 GHz. Antenna gain In the simulation result of figure 3 shows that the gain from the antenna had a fixed tendency of 15 dBIC. In the C-band at working frequency range from 5 to 6.7 GHz. The stability of our antenna gain at the working bandwidth of SAR is very advantageous because the amplitude of the chirp signal sent will be the same value. In addition, the stable high gain will be benefit for our UAV power budget, since it reduces the needed transmitter power as stated in the ring radar equation, as mentioned in the literature number 24 to 25. Next is our radiation pattern. Figure 4 illustrates the radiation pattern of antenna at the frequency 5, 5.3, and 5.8 GHz. Specifically in the A and H bit direction, figure 4A and 4B shows radiation pattern at 5 GHz RHCP and LHCP in the A and H field. The gain in broadside were 15 dBIC in both RHCP and LHCP. With very low cross polarization, less than -20 dB, notably at 5.3 GHz, figure 4C and D, the antenna achieved a half power beamwidth of 28 degrees and 28 degrees for the A and H feet respectively. This indicates that the antenna had a relatively focused radiation pattern, allowing for a narrower coverage angle. Additionally, the cross polarization at 5.3 GHz was observed to be very low, indicating that the antenna effectively maintained polarization purity. It was also maintaining the same good characteristic in gain, half power beamwidth, and cross polarization at 5.6 GHz, as shown in figure 4A and 4F. Yeah. Okay. Moreover, the analysis revealed that the antenna exhibit a minimal side lobe response, with side lobe level below -20 dB. This characteristic was highly advantageous, particularly in applications such as SAR system, where side lobe reflection can introduce unwanted noise and degrade image quality. The low side lobe value observed in the radiation pattern ensure that the antenna minimizes side lobe interference, enhancing the accuracy and clarity of the SAR system imaging capabilities, as mentioned in literature number 26, also explain about that. For comparison purposes, the performance of this horn antenna was evaluated alongside several C-band CPSR sensors, and the results are presented in Table 2. The horn antenna demonstrated a moderate gain of 15 dBIC, making it well suited for Malay SAR type UAV that operate at medium altitude and possess a smaller aperture field area compared to antenna design number 2 and number 3. Additionally, the horn antenna features a significantly wider axial ratio and S11 bandwidth, resulting in superior sound resolution compared to design number 2 and number 3. Okay. As conclusion, the design and simulated antenna using CST 2022 software exhibited impressive capabilities featuring circular 2 polarization to the right and left with an axial ratio below 3 dB across the frequency range of 4.4 GHz to 6.25 GHz. Additionally, the antenna achieved a medium range gain of 15 dBIC, rendering it highly suitable for deployment in medium UAV distance, particularly in the Malay UAV class. The incorporation of dual polarization in this antenna enabled full polarimetry capability while maintaining a compact aperture area. The utilization of this sensor in UAV application proved advantageous as it caters to limited space and weight constraint, enhancing the overall efficiency and practicality of the system. Acknowledgement. Authors, thanks to the KST Soekarno Cibinong Bogor Brain Computing Lab for providing access to the professional CST 2022 software, which play a crucial role in our research. We would also like to extend our appreciation to the Research Center of Aeronautic Technology, National Research and Innovation Agency for the invaluable support in the funding of the horn antenna research through the home budget funding program in 2022 grant number 23. Here's the references. Okay, here's the equator.